Hey guys, we're going to see how this works. I'm going to try to record a little video just to bring you up to speed on what we talked about in class today so that you don't feel like you're behind tomorrow. I don't know if I can switch back and forth between this program and the PowerPoint, but I'm going to try, so we'll see what happens. Okay, the first thing that we talked about is your little electromagnet investigation, and what we're interested in is the why of why you saw what you saw. And just a few definitions here. I think the video is still running, so we'll call it good. Just a few definitions here. When you talk about electricity, the three basic terms that we're most interested in are voltage, current, resistance. And in using our little analogy that many instructors use too, where an electric circuit is like a garden hose, okay? The force that pushes the water through the hose is the water pressure. That's like voltage in an electric circuit. That voltage is what causes the electrons to move. It's also abbreviated as EMF, which means electromotive force. Current is actually a rate unit. The ampere, or amp, means a certain amount of charge per second. And that's what current measures, is the flow of electricity in a circuit. It's like the water flow in a hose. If I say, gallons per minute, that's like saying amperes in electricity, except an ampere would be coulombs per second, and a coulomb is a particular amount of charge. So an ampere is really a rate unit with respect to time. And resistance is literally whatever resists the flow of electricity. So if you can think of that analogy, like if I have a fire hose, a 2-inch fire hose versus a 1/2-inch garden hose, with less water pressure, I can get a huge amount of flow out of a fire hose. Okay, if I wanted to get the same amount of flow out of a 1/2-inch garden hose as I was getting out of the 2-inch fire hose, it's going to take a lot more water pressure to make that flow rate happen. So that is the same as with an electric circuit. If the resistance is increased, you need more voltage to get the same amount of current. And then this term flux, if you're a welder, flux has an entirely different meaning, but in physics, flux means the total electric or magnetic field that's passing through a surface. So literally, the number of field lines that are passing through a surface is a description of electric or magnetic flux. So these are the 4 questions that we discussed today with respect to what you saw when you did the electromagnet investigation. Why would the number of wines affect the strength of the magnet? Why would the voltage affect the strength? Why would the wire material affect the strength? And how do you explain what happens with the string? Why would the wire size or gauge affect the strength? Essentially, here's what we came up with in a nutshell. Anything that increases the flux, which basically is to say increases the current, with the exception of number 1, but it's sort of the same principle. On number 1, the number of wines, you're not literally increasing the current in the wire if you increase the number of wines. However, you are increasing the amount of charge that is in a particular area around that core, which is increasing the strength of the electric field, and therefore increasing the flux moving through the core, and it's a stronger magnetization. So it would increase the strength of the magnet by putting more charges around the core. In number 2, the voltage, more current, more charge, more flux. Okay, you've got a stronger electric field makes a stronger electromagnet. Number 3, why would the wire material affect the strength of the electromagnet? Well, there's 3 materials that you compared. You had copper, aluminum, and string. Obviously, with the string, it didn't pick up any iron filings. That's because string is not a conductor of electricity. It's not a metal. it won't conduct electricity, and if you don't have any current flowing, you have no electric field. So there would be no magnetization of the core, nothing will happen. Okay, but between the aluminum and the copper worked better. The reason why is because there are different strengths of conductivity within metals, and copper is a better conductor of electricity than aluminum. Now, one point that we did talk about is, even though that is true, it's actually aluminum that's used in the overhead transmission lines, and as far as I'm aware, the main reason is because of weight. That the density of aluminum is about 3 times less than that of copper, and if those lines were copper, it would put a tremendous tension load on the poles and the wires. So for the weight factor, we use aluminum instead of copper, even though copper is a much better conductor. Okay, but essentially the same thing. Aluminum has more internal resistance, which means a lower current, less strong electric field, means less strong electromagnet. And the last one, why would the wire size or gauge affect the strength of the electromagnet? This is the fire hose versus garden hose analogy. Bigger gauges of wire mean less internal resistance. If you're going to pass more current through a circuit, you need a bigger wire. Electricians have to be very cognizant of this. I mean, if you're wiring a house and you don't know how much current is going to flow through a circuit and you use too small a gauge of wire, you might end up burning the house down, because smaller wire means more resistance, which means more heat generation, and the wire will burn through or could get hot enough to set something around it on fire. So it's very, very important to understand what gauge of wire you need for a particular current running through a circuit. So bigger gauge, more current, less resistance, stronger electric field, stronger electromagnet. Okay, now how does this relate going forward to talking about chemistry and atomic structure? Well, as I had mentioned, throughout the 1800s, kind of the new thing in science was electromagnetism. The battery had just been invented in the very early 1800s, and this was the first time that scientists had access to a steady electricity source. Before that, if you recall watching the video before Christmas where it was Mysteries of Matter Part 1, and you see Joseph Priestley cranking the machine in there that's producing sparks, that's called a Wimshurst generator, and it is an electric generator, but it's a static generator. And it's basically like a big spark plug. It does not produce a steady, continuous flow of electricity. So we didn't have that capability until Alessandro Volta invented the voltaic pile in the early 1800s, which was followed pretty quickly after by the Daniell cell, which was an improvement and even a smoother battery that produced a better continuous flow. So people began to experiment hot and heavy with electricity, and they were building a lot of stuff and doing a lot of experiments with electricity without really understanding a lot about the nature of electricity. One of these things that was invented was a piece of technology called the CRT tube, which stands for cathode ray tube. And here is a picture of it. Let's see. Okay. A cathode ray tube, this was the precursor of the television. Back in the before time, in the long, long ago, when people didn't have flat screen TVs and they had the big TVs that were thick and heavy, what is in those TVs is a CRT tube, a cathode ray tube. And this is a very, very simplified version of a cathode ray tube. But all that it basically is a glass tube that has 2 contacts. You've got an electrode connected to a metal plate here, and then another electrode here. And this white thing is just a strip of paper that's there for a background, but there is no other matter in the tube. It is a vacuum tube. Everything has been sucked out of it. There is no air, no gases, no anything between these contacts. However, when you hook them up and put a high voltage to it, then this is what happened. Put a high voltage to this tube, whoa, and this green beam appears. Okay, where is the beam coming from, and what is the beam composed of? That is the question. Well, in 1897, a physicist named J.J. Thomson did some experiments with this beam, and what? Okay, so if you put a magnet next to the beam, it actually deflects it. Okay, and one pole of the magnet will deflect the beam one direction, and then if you flip the pole of the magnet, it will actually deflect the beam the other direction and attract the beam instead of repelling it. So that was some very interesting stuff that was going on there with that cathode ray tube. Okay? And the question is, number one, what did that tell us? And number two, how did it lead to learning anything about the atom? Well, first of all, you can tell that if the beam is deflected by a magnet, it's either magnetized or it's electrically charged. Okay, that much is obvious. Otherwise, the magnet wouldn't do anything to it. The second question, what is the beam? Well, that was the real question. Because at the time, we didn't know anything smaller than atoms. I mean, we still thought that atoms were the smallest pieces of matter possible. And the smallest thing known was a hydrogen atom. Now, it was known that hydrogen atoms could be charged. It was not known how a hydrogen atom would become charged, but we knew that they existed, and certain properties about them had been measured. So we could do some measurements on the beam, or J.J. Thomson could do some measurements on the beam and compare it to the hydrogen atom and see what he found. So the first thing that he decided to do was this, that instead of using a magnet, got to get back to my deal here, okay? That instead of using a magnet, he hooked it up to two electrical plates, okay, and put an electrical field across the beam and shot the beam through it. And what he found is the beam would still be bent, okay, and it was bent away from the negative plate toward the positive plate, which had to mean the beam was negatively charged. It was somehow carrying negative charge. Because opposites attract, it's going toward the positive, away from the negative. The beam has to be negatively charged. So that much he knew. Now, the next thing that he set out to find, and this is a little bit more difficult to explain, but the purpose in our talking about this is to try to explain the line of reasoning that led us to why we think the atom is the way that it is. So the next thing he had to do was compare it against that charged hydrogen atom. And here was the basic thinking behind this. There are pretty much two laws or two versions of the same law that he used to do this. The first is Newton's second law of motion. Force equals mass times acceleration. Pretty simple relationship. You can imagine, okay, if I apply a force, if I go out in the parking lot and I try to push a Chevy Cobalt as opposed to trying to push around a full-size pickup truck, I'm going to have a lot easier time moving the Cobalt than I am the pickup truck. I can give it a greater acceleration because it has less mass, right? It takes a greater force to give that acceleration to a larger mass. That, in essence, is what Newton's second law says. Okay, now you can sort of recast Newton's second law to apply to a charge in an electric field, which this just says force equals the field strength times the charge of the particle. So a particle in an electric field, if it has a greater charge itself, will experience a greater force, or if it's in a greater field strength, then it will experience a greater force. So when he takes that back to the CRT tube, okay, he knows that the bending of the beam could actually be two different things happening here. That the beam could be bent less if the particles are heavier because of Newton's second law, and the fact that whatever force is being exerted on it from the field still will not be able to bend particles of heavy mass very much. Or it could be that the bending of the beam depends more on the charge of the particles in the beam. he can't really tell which one it is. Okay, Thomson is really not able to come up with a definitive answer for that on his own, but what he is able to do is something very cool. Because both of these equations describe a force, you can set them equal to each other and then rearrange it to get an equivalent ratio, which would be the mass of the particle over the charge of the particle equals the field strength over the acceleration. Now, he could not directly measure the acceleration. He didn't know how fast the beam was moving, so he didn't really know how long the particles were staying in that electric field, but he could reason that he didn't have to know that because the amount that they were being accelerated or curved as they went through the field was going to be seen in the angle that the beam was deflected. So the angle of deflection was proportional to the acceleration. So he could substitute that in for acceleration and come up with this ratio, which is known as the mass to charge ratio. This in and of itself wasn't able to tell him definitive properties of the particles in the beam, but it did tell him something. Compared to the charged hydrogen atom, the mass-charge ratio of these particles in the beam was about 1,500 times greater than anything that had been measured to that point. Now, there were two possibilities for that, two hypotheses that could both explain that behavior. Either those particles were 1,500 times smaller than the hydrogen atom, or the particles carried 1,500 times more charge than the hydrogen atom. And it would not actually be Thomson that could figure this out directly. It took another scientist with another super cool genius experiment to actually decide between those two hypotheses and determine whether they are very small particles or if they are supercharged particles compared to the hydrogen atom. And that's where we left off, and that's what we're going to kind of go over tomorrow and explain. So I hope that y'all are feeling better, and we'll see you tomorrow.